So we come to the session 6. So we know all the definitions of a ring. Again, I told you what is the definition. Again, you know the meaning of integral domains. So now we are going to prove in a Z. What's the n in contains either a composite number or a prime number. If n is a prime, then Z n. If n is a prime, suppose I instead of n I took p, means p is a prime, zp is a field under additions and multiplications. Now I am going to prove a theorem: the ring Zn under additions and multiplication is an integral domain, hence the field if and only if n is a prime integer. So we know, if for example, suppose if we take Z7, what are the, I'm omitting the element 0, 1, 2, 3, 4, 5, 6. So here 0 is not appear. Here if you multiply any two integer, it's a non-zero. Suppose 1 into 2, 2 into 1 is a 2. Suppose 3 into 4, I'm saying Z7 equal to 1, 2, 3, 4, 5, 6. So 3 into 4 is 12. 12 is 5. Again 4 into 5 equal to 20. 20 we can write 6. Here 3 is not equal to 0. 4 not equal to 0. The product is not 0. Product is 0. Here I'm saying this is integral domain. So integral domain is also a commutative as a unity without each element as inverses. It inverse. Now we shall solve first that Z is an integral domain if n is a prime. So we shall prove n is not a prime. We know the definitions. Your integral domain is a field. So if integral domain is field, is true. Suppose if we take n is a composite number. If n is a composite number, suppose I can take Zn is a not integral domain. If n is a not a prime, is not an integral domain. Or n is a prime if Zn is a zero divisor. So if n is a not a prime, means n is a composite. There exists a two integer. So there exists two integer means if you take a composite number can be, for example, 15 is a composite number. 15 can be written as 3 into 5. 15 can be written as 3 into 5. So with here 3 suddenly less than 1, less than 3, less than 15. Again, if you take a 5, 1 less than 5, less than 15. See, divisor is always less than that number. Means n is equal to m into l. M into l means product. You can add. Suppose if we take a 15, 15 can be written as 3 into 5. Here m is 3, l is 5. Suddenly 1 less than m, less than n. 1 less than l, less than n. Suddenly m not equal to 0, n not equal to 0 belongs to Zn with m into n equal to 0 under multiplication. This implies that m is a zero divisor in Zn. This implies Zn is not an integral domain. Zn is not an integral domain. Hence Zn is an integral domain. N must be a prime. Because by using the integral domain, we can prove this is a field. Conversely, we shall show that n is a prime. This implies Zn is an integral domain. Zn, for example, you are taking the prime number. If you take a prime number, what's a prime? 7. 7 is a prime. We can write 7 can be written as 1 into 7 only. Suppose if you take a 5, 5 can be written as 1 into 5, like that. So 1 not equal to 0, 5 not equal to 0. So we shall show that n is a prime. This implies Zn is an integral domain. And multiplication and whatever may be either addition or multiplication, n is commutative with unity. It is sufficient if so that n is a prime. This implies Zn has a no zero divisor. What's a no zero divisor? Means for example 1 not equal to 0, 3 not equal to 0. The product should not be equal to 0. No zero divisor. Simply I say without a zero divisor. Let I take a into b equal to 0. A into 0 for a and b in a Zn. This implies A in B, you can write A into B equal to nk for some k. So for some k in belongs to Zn. So this means n divides AB. N divides AB. By using the division algorithm, n divides A or n divides B. What means n divides A and divides B? Because if n is a prime, n, if suppose n is a prime, n can be written as 1 into that times. N is a prime, n can be written as 1 into that time. So 1 into that time means that number only divisibles. If A equals 0 or B equals 0, A B net less than n means A cross B equal to 0. That is A equals 0, B equals 0. So if n is divide that number, so either n divides A or n divides B, either of them. So that is if A equal to 0, B equal to 0, since A comma B less than n, that number. Suppose if we take 15 can be written 3 into 5. So suddenly 3 less than 15, 5 less than 15. Therefore, n A cross B equal to 0, that is A equal to 0 or B equal to 0. So without a zero divisor, hence Zn has a no zero divisor, and therefore it is an integral domain. Further, as Zn is a finite set, if n is a prime, then it is a finite integral domain. Therefore, it is a field. Zn is a finite set means we take Z15, Z13, whatever may be, Z11 is a finite. If n is a prime, means 15 is a 13 is a prime, 11 is a prime, 7 is a prime, this type. It is a finite integral domain. Therefore, it is a field. By using the same theorem, one more theorem you can prove. Let R be a commutative ring with unity. Then R is an integral domain if and only if the set non-zero element means R star, the set non-zero element R of all non-zero element of R is closed under multiplications. So closed under multiplication. If prove simple, let R be an integral domain. Let A comma B belongs to R star. A comma B belongs to R star means A not equal to 0, B not equal to 0, non-zero element. D and arbitrary. This implies A not equal to 0, B not equal to 0. This implies the product not equal to 0. A not equal to B. And suppose if we take P comma 7, 3 into 7, again not 0, that belongs to ring R star. So product should not be equal to 0. Since A into B does not belongs to R star. Thus, R is closed under multiplication. This is obvious. Suppose if we come to the close under multiplication, suppose in case of that, let R star be a close under multiplication. Therefore, for all A comma B belongs to R star, this implies A into B belongs to R star. That is, A not equal to 0, B not equal to 0. This implies the product is not equal to 0. Therefore, R has no zero divisor. Hence, it is an integral domain. See, this all holds in the non-zero elements, because if you take a prime, the prime, you should omit the zero element here, Z7. If it's Z7, you choose that number should be 1, 2, 3, 4, 5, 6. You are omitting the 0. So you multiply any numbers. Yeah. So Z7 should be equal to 1, 2, 3, 4, 5, 6. So 3 into 4 should be non-zero. The product should be 5. Because if you get a 12 is divisible by 7. Left remainder is 5. Again 4 into 5. 4 into 5 is 20 equal to 6. 20 is divisible by 7. Remainder is 6. Like that. If you multiply any number, should not be a 0. Should not be. That's why I am saying A not equal to 0. B not equal to 0. The product should not be a 0. Yeah, this is integral domain without zero divisor. Should be no zero divisor. Hence, it is an integral domain. By using the same property, we give one more simple theorem called in an integral domain, the non-zero element form a semi-group with respect to multiplications. You know, semi-group means only two operations hold: closure property and associative property. Closure property and associative property. Suppose if you take two elements in a non-zero ring in R star, if we take a two element, non-zero element, so closure property is what? A is there in R star, B in R star, the product in R star, A in R star, B in R star, A plus B will hold. A into B is also in there. This pro. B into A is also old. That is a closure property. This arbitrary implies A not equal to 0, B not equal to 0. This implies AB not equal to 0. Since R is an integral domain. Therefore, the R star is closed under multiplication. Now, these are a simple theorem regarding by using a integral domain. By using the integral domain, Zn we can prove is a field. By using integral domain, Zn is a integral domain. Domain.